Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 5.13. The problem statement says, a nitrogen rotometer is calibrated by feeding nitrogen from a compressor through a pressure regulator, a needle valve, the rotometer, and a dry test meter, a device that measures the total volume of gas that passes through it. A water manometer is used to measure the gas pressure at the rotometer outlet. A flow rate is set using the needle valve. The rotometer reading, phi, is noted, and the change in the dry gas meter delta V for a measured running time delta T is recorded. Then they give a diagram, kind of like my diagram, except for theirs is better. And the following calibration data are taken on a day when the temperature is 23 degrees Celsius and barometric pressure is 763 millimeters of mercury. Okay, and then they give these specs here. Okay, and then they give us this table, not including this row. I added that later. Prepare a calibration chart of phi versus volumetric flow rate in standard units. The flow rate in standard centimeters cubed per minute equivalent to the actual flow rate at the measurement conditions. Okay, so this is our volumetric flow rate. We get that by saying, okay, delta V divided by delta T gives us a volumetric flow rate. So we have a volumetric flow rate, and then we just have to convert the units, right? So for a certain rotometer reading, then we've got a flow rate, okay? Makes pretty good sense. We got 3 points, so we'll check to see if it looks like a line. So I put all these points into Excel, and I see, yep, looks like a line. Okay, looks pretty close to a line. So we're going to assume that this linear model works, where x is phi and v is the volumetric flow rate. We get our m and v values here, and that is our volumetric flow rate based on the rotometer reading. Okay, here's the problem though. They said they wanted it in standard velocity. Okay, so it's standard conditions. So if we change the pressure and temperature so that they're standard temperature and pressure. Okay, so in order to do that, we need to say, okay, the volume is proportional. That's what, it's this proportionality constant here. And we know that V and our volumetric flow rate and our standard volumetric flow rate are going to be slightly different based on these standard temperatures and pressures, but the molar flow rates are the same. Okay, so we just say that these things are equal to each other, like we set up here, and we can calculate what our proportionality constant is. And in order to make these proportional, we just divide the temperature by the standard temperature and the standard pressure by the pressure, the actual pressure. Okay. So we actually don't know what the actual pressure is though, because they never told us what the manometer reading is. We don't know what the gauge pressure is. Remember that there was a pressure gauge right here? They said that was a water manometer. They never gave us any information about this, so we don't have what the pressure is inside of the system. So that is a problem. But we'll just kind of continue as far as we can without that information. Okay, so we plug this equation into our setup here. We're using millimeters of mercury. Okay, so it's important to write down what units you're comparing to, because this barometric pressure needs to be compatible with whatever pressure units we end up using in the gauge pressure. So if our gauge pressure needs to be in millimeters of mercury is what I'm getting at. And so does our standard pressure if these units are going to cancel out. Okay? So if our gauge pressure is in millimeters of mercury, then this is our proportionality constant right here. Okay, so then we just plug our proportionality constant into this equation. Say our standard flow rate is equal to this flow rate divided by that proportionality constant, and you just plug it in substitution. Okay, so that's our relationship. We've got our certain rotometer reading, and then we have our certain gauge pressure that they never give to us. But this is the equation we would use in order to calculate what the standard flow rate was. Okay. Then in part B, it says, suppose the rotometer valve combination is to be used to set the flow rate to 0.01 moles of nitrogen per minute. What rotometer reading must be maintained by adjusting the valve? Okay, so you adjust the valve and you get a certain rotometer reading, right? So we've got our rotometer reading here, and this is the flow rate. Now they're saying, okay, do it backwards now. Okay, well, this is the ideal gas law at work again. We can say, okay, we have this molar flow rate. We need to know what the pressure is and what the temperature is. Well, I guess we're just assuming that we're at the same conditions because they didn't give us new conditions. Or I don't know if we were supposed to assume it's standard conditions or whatever. Either way, we still don't know what the gauge pressure is. So we don't know what the pressure is inside the system for this setup either. So if we assume, I guess if we assume that it's the same, I mean, whatever the same is, gauge pressure, whatever the same is. Okay. This time I converted it to pascals. So we've got our newtons, we've got our R reading. If we convert this into pascals, the gauge reading into pascals, it needs to be compatible with whatever R units you're using. So if you're using joules per mole Kelvin, then you would need to use pascals here for the pressure. Okay, so that's why I converted this into pascals for the absolute, or for the atmospheric pressure. Okay, and then you just substitute this in again as well. So this would give us what the molar flow rate that we could get based off of our reading here, if we knew what the gauge pressure was. At the same conditions, so that would be at the temperature that we were at before, 23 degrees Celsius. So, and what if it was at the same gauge pressure? Okay. If you guys found out a way to get around this problem about not having any information about the rotometer, or if you feel like this setup was kind of confusing, just let me know in the comments. Also, I'm serious if there are any problems that you'd like me to work on in this book, if you'd prefer not to be in chapter 5, if you want to work in a different chapter, or if you just have another book. I'm pretty familiar with lots of engineering materials, so if you prefer, I'll even look at another book. If I got that book, I'll try and do some problems, or just from a different subject, even if you don't have the book. If you want to look at different material, I can take a look at that. But anyway, that's the end of 5.13. So thanks for watching. I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Your feedback's valuable. I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.